We are going to dive straight into how we derive the equations of motion. That is motion in a straight line. We have 5 equations of motion, and we are going to, in this video, I'm going to show how we derive the equations of motion. But before we get into the derivations, I would like to take you through the overview of where we are going. To begin with, the parameters we are going to consider are displacement, which is going to be denoted by S. We have the initial velocity, which will be denoted by U. We will have the final velocity, which is denoted by V. Then we will have the acceleration, denoted by A, and then the time, denoted by small t. Now, what are these equations that we are trying to derive? The equations of motion are basically 5. We have the first equation of motion, which is V is equal to U plus AT. We have this one, we have that one. For displacement, we have this one for V squared is equal to U squared plus 2AS, and then finally that one. But in all these 5 equations, you notice that in each and every equation, there is a certain parameter that is missing. If you look at these parameters that we considered at the beginning, the displacement, the initial velocity, the final velocity, the acceleration, and the time, if you're to examine each and every equation, there is a parameter missing, one parameter of all. If in a certain equation you'll find that all these 4 parameters are there and S is missing, then in another equation you'll find that U is missing and all the other parameters are there, or you'll find T missing and all the other are there, and so on. And so it means that as we are deriving these equations, we have to put in mind in some of our substitutions that there are certain parameters that we will be deliberately leaving out for us to be able to attain the equation we're trying to derive. For example, if you look at the first equation of motion, it is S that is missing. There is no displacement here. But this displacement is in all the rest of these equations. If you look at this second equation, we have A missing. The acceleration is not represented, but acceleration is in all the others. In the third equation, you're having final velocity missing, but final velocity is represented in all the other 3. Then likewise here, time in this equation is missing, but it is represented in all the other equations. And finally, even in this final equation, you're having U missing, but this U is represented in all those other equations. So we'll get started with first coming from where acceleration comes from. Now, acceleration by definition, from our theory, we know that acceleration is the rate of change of velocity. Now, if we are to use an illustration as in our screen diagram below, the write-up says that if an object is to move in a straight line from 5 meters squared, and after 3 seconds its velocity is 11 meters squared, this is what has been illustrated here, that this object starts moving from 5 meters squared. So it means that 5 meters squared is its initial velocity U. Then it moves, and after 3 seconds, so after traveling for 3 seconds, this is from 0, after 3 seconds, its velocity is 11 meters per second. So it means that it moves, and its final velocity here, which is V, is going to be 11 meters per second. Then it means that the object was accelerating. It accelerated from an initial velocity of 5 meters per second to a final velocity of 11. And it means that when we draw this graph of velocity against time, the velocity time graph, when we draw this graph, the gradient of this graph represents the acceleration. And now, to find the gradient, of course, the formula for gradient is going to be change in y. So what is changing in y? The final velocity 11. To get this acceleration, the slope, acceleration is going to be equal to the change in y, which is 11 minus 5. Divide that by the change in x. The change in x, of course, it's the final minus the initial, which is 3 minus 0, giving us 3. 11 minus 5 is 6. Divide that by 3. Now this 11 minus 5, of course, is in meters per second, and this time is in seconds. So 6 over 3 is going to give us 2. Now 2 is in meters per second squared. Of course, this meters per second squared is coming from here. Meters per second divided by second gives us meters per second squared. So now this 2 meters per second has been gotten from the slope of this graph, and this is the acceleration. Acceleration is the rate of change of velocity, because as we can see here, we are having velocity being divided by time. So the rate of change of velocity is what has given us this acceleration. And so we are going to use this kind of analogy to derive our first equation of motion. Now looking at that, our first equation of motion, still we are going to consider an object. It is moving from initial velocity u to final velocity v, and when you draw a velocity time graph, this is velocity in meters per second, this is time in seconds. So to find that slope, we know that right here, the slope of this graph to get the acceleration, the slope is going to be change in y. Now of course the change in y is the final minus initial, the final velocity v minus the initial velocity, which is u, divide that by the change in x. The change in x, of course, it's the final time, which is t, minus the initial time, which is 0. This is supposed to give us the slope, which so happens to be the acceleration. So when we make this a flat equation, this becomes v minus u over t is going to be equal to a. Multiply t on both sides. This goes with that. We remain with v minus u, giving us a t. When we make v the subject of the formula, v becomes, u goes the other side, u plus at. Just here, v minus u over t is equal to a, and this step comes to that. This is how we arrive at this, which is that. Now that makes up our first equation of motion, v is equal to u plus at. So now we are going to go on to the next equation of motion. Now still the next equation of motion, we are still going to use this very graph. From our theory, we know that the area under a velocity time graph represents the distance traveled by that particular particle. And in this case, if you look at this graph, if I'm to draw that right there, it is going to form what we call a trapezium. So now the trapezium, it means that if we are to find the area of this trapezium, the area of this trapezium is going to give us the distance traveled by this particle from that point, the distance traveled by this particle from initial velocity u to final velocity v. So the area of a trapezium if we are to change this graph like this, this is how the trapezium looks like. And so it means that as far as our trapezium is concerned, our value of a, the height of the trapezium is going to be that one, this, and this will probably be our value of a, and this is our value of b. And now the area of a trapezium is given by, area of a trapezium is going to be a half h into a plus b. And from our trapezium earlier, I'll redraw it here. Now looking at our trapezium here, if I'm to put it upright, the way it should look like, this is going to be our value of h, and our value of h is definitely coinciding with the length 0 to t, so this is our value of t right there. Then here we are looking at it this way. Then here it is coinciding with u, because from here to there the length is u, initial velocity, so our value of a is corresponding to the value of u, and then our value of b here is corresponding to our value of v, which is v. This is v, this is u, and this is our value of t. And I have extrapolated this and I have put it there like that. So it means from our area it's going to be a half h into a plus b, which is going to be a half times t. Our value of h corresponds to the time into the initial velocity u plus the final velocity, which is v. And definitely when we rearrange this, this becomes u plus v over 2, and all this is times t, which is that one. So this makes up our second equation of motion from that graph. If we are not to use the graph to find the second equation of motion, we can relate it that we know that average velocity is going to be initial velocity plus final velocity, divide that by 2. And also another formula for average velocity is displacement, divide that by time. So it means that we are going to equate this to that. So that's how we end up with displacement over time is equal to average velocity, which is u plus v over 2. Since So displacement is denoted by s, divide that by time, is equal to u plus v over 2. Then when we make s the subject of the formula, we end up with s is equal to u plus v over 2 times t. And this is just an alternative way, or this is another way we can find our second equation of motion. And so we'll go ahead and derive our third equation of motion. Now, our third equation of motion, we are still going to consider this very graph, but we are going to look at this graph. We are still going to try and find the area under this graph, but only that this time around, the area under this graph, instead of finding the area as a trapezium, we are going to divide this area into two. And so we are going to get the area of this triangle, and we add that area to that rectangle. And then when we add the two areas, we are going to get an expression that is going to give us our next equation of motion, the third equation of motion. So here is how we are going to do it. We are going to get the area under this graph, but we are going to divide it like that. So we have area of A and area of B. And definitely, of course, here, the area of this first portion, our value of A, is going to be a half. This is a triangle, and we know that the formula for finding the area of a triangle is a half times base times height. So that is a half times base times height plus the area of the rectangle, which is length times width. And of course, in this case, it's definitely going to turn out to be that our A, which is the distance, because our area under this graph is the distance, so distance S is going to be a half times base. Now the base here is t, because the distance is t, times height. Now the height here is v minus u. This is v minus u. Where is the v minus u coming from? Of course, v minus u here is the distance from here to here is v. The distance from here to here is u. This is v, this is u. So to get this remaining distance, which is corresponding to that, it's going to be v minus the u to get that remaining distance. That's how we come up with that v minus u plus, now length times width. This is a triangle, a rectangle. Our value of length is, that's our length, which is t, and our width, which is u. So that's how we come up with that step. So from here, it's going to become a half. Now this AT has replaced that into this. So it is a half times v minus u, which is actually this whole thing. This whole thing is that, this whole thing becomes AT squared plus ut. Now how does this come about? Now we know that acceleration is the rate of change of velocity. So we know that acceleration is the rate of change of velocity, and by that we mean that acceleration is going to be equal to, this is the definition of acceleration. Acceleration is the rate of change of velocity. Final velocity minus initial velocity over t. Now when we make this a flat equation and we multiply t on both sides, we shall end up with at going to be equal to v minus u. So you realize that this v minus u, which is here, is the same as 80. So we get this v minus u and replace it with 80. So it means that when we get from this step, let me rewrite it here. When we come from this step, which is a half t into v minus u plus ut, the next step after this is going to become a half times t into v minus u. Now v minus u is the same as 80, so instead we shall write 80 right there plus ut. So now 80 times t becomes a half a t times t is t squared plus ut. So this is how this a half 80 squared plus ut, this is how it comes to be like this in the next step. So now when we get to that, we have formulated our third equation of motion. In this case, our third equation of motion is that one. It shows that s is equal to ut plus a half at squared. That's our third equation of motion. Alternatively, we can find the third equation of motion by substituting. So for us to get our third equation of motion, the fourth equation of motion, and the fifth equation of motion, those other three equations also are going to be derived using substitution. So now the substitution is going to be entirely based on which parameter do we want to eliminate. We eliminate that parameter by substituting the first two equations. Now the first two equations of motion we got were, now these are the first two equations of motion we got. We got this first equation of motion using the graph. We got this second equation of motion also using the graph. When we got this first equation of motion, we were basically depending on the theory that acceleration is equal to the rate of change of velocity. From its definition, from the definition of acceleration, we were able to derive this equation. And then for us to be able to get this second equation of motion, we were able to get it by looking at the area under the graph. So all these other three equations of motion shall be gotten by substituting these two. So it means that if we want to get the value, the third equation of motion, we are simply going to eliminate v in this equation. So we are going to get the value, the expression for v, which is this one, and substitute it here to get this one. If we are going to, for us to get the fourth equation of motion, it means we need to eliminate t. If we are to eliminate t, it means we are going to get this value of t here, make t the subject of the formula in this equation, come and substitute the value of t here, so that we eliminate t in this expression, and that's how we are going to get this expression. Likewise, in the fifth equation of motion, we are eliminating u. So it means we're going to get u here, get this equation, the first equation, make u the subject of the formula, then get the expression for u in this equation, substitute it here, and then we'll be able to get the fifth equation of motion, like that. So you can do it any way you like, but the main idea behind is that we are formulating these equations based on eliminating the parameters that you see right here. So we'll go ahead, dive straight into it. So it means that for us to substitute for to get the next third equation of motion, we are going to get this equation of motion, which is the second equation of motion we derived earlier, and then we eliminate v. When we eliminate v, it means that we are going to eliminate v from our first equation. Our first equation of motion was v is equal to u plus at. And our second equation we got was this one. So we are going to get this value of v and substitute it right there. When we substitute it right there, u plus at is what we put here. So it's going to be u plus v, which is equal to u plus at, divide that by 2 times time. And so from there, we shall end up with u plus u is 2u, and then plus at, which is 80. And of course, when you multiply this times time, it becomes 2ut, and then 80 times time becomes 80 squared. All this divide by 2. And then that's how we end up with our third equation of motion. So we're going to use the same idea. We're just going to play around with the first equation and the second equation to substitute them to make the fourth equation of motion. Again, our fourth equation of motion, we are going to get our first equation, which is v is equal to u plus at. And when we make t the subject of the formula, it becomes t is equal to v minus u over a. So we are going to get this expression of t and substitute it in the second equation we derived earlier. So we are going to replace this value of t. So when we put this expression here, this value of t has been replaced here. So it's going to be v plus u over 2, then v minus u over that. So when this multiply that becomes u plus v into v minus u over 2 times a, which is 2a. From our mathematics, this is difference of two squares. So this is the same as v squared minus u squared. Of course, when you open brackets here, you end up with this expression. Divide that by 2a. That is going to be equal to s. And when we make this a flat equation by multiplying times 2a on both sides here, even here times 2a, we shall end up with the expression of 2as is equal to v squared minus u squared. When we make v squared the subject of the formula, we shall end up with v squared is equal to u squared plus 2as, which is our fourth equation of motion. Our fifth equation of motion, we shall still use the same technique by playing around with the first two equations of motion. Still, our first equation was v is equal to plus at, and then when we make u the subject of the formula, it's going to be v minus at. So we substitute this u, value of u, in the second equation of motion, which is u, that u there. So when we get this u and substitute it right there, it's going to become the value of u, we put v minus at in its place, plus v, divide that by 2. Of course, when you open brackets with the t, multiply it through vt minus at squared plus tv, divide that by 2, you end up with your real tv plus tv is equal to 2tv minus at squared, which is that, minus at squared, divide that by 2. And definitely we will end up with our final expression. Our final expression is going to be s is equal to tv minus a half at squared, and that's our fifth equation of motion. So again, throughout, these were the parameters we were considering: displacement, initial velocity, final velocity, acceleration, and time. And each of those equations we were trying to derive, all these equations we derived, you saw that our first two equations were the ones that we derived from scratch. The first one we derived using the definition of acceleration. The second one we derived using the concept that the area under the graph is equivalent to the distance traveled by that particle. And then all these other three equations of motion were derived by substituting these two. We substitute these two in such a way that we eliminate v, we eliminate t, and we eliminate u in these substitutions of these two equations to be able to attain these other three equations. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia, helping you manifest excellence.